So in this video, we're going to be doing Born-Haber cycles, and Born-Haber cycles are a process of studying the elementary steps that go into the formation of ionic compounds. All right. What it has in common with what we did in the previous video is that you're basically taking an overall process and you're breaking it into its individual steps. And you're saying that the overall enthalpy change of the overall process is just the sum of adding up the enthalpy changes of the individual steps. For example, in the last video, we talked about the process of solubilizing an ionic compound. And whenever something dissolves, you could consider it nothing but the combination of first breaking it apart into its individual gas ions, and then dissolving those individual gas ions in water. All right, and each of these has their own associated enthalpy change. Which is another way of saying would that individual step give off heat or would it absorb heat? All right, and we could calculate the overall heat change just by summing up those parts. All right, so in a Born-Haber cycle, this is the best way to describe this is to compare this to something that we talked about earlier, which is the heat of formation of a compound. All right, so the heat of formation of a compound is the energy released when the compound is formed from its component elements at their standard state. All right, so for example, if we were to do this for water, all right, recall that first of all, we have to take the elements in their standard state and under standard conditions. So that would involve taking hydrogen gas, all right, because it's hydrogen in its elemental form is a gas at room temperature. All right, we do the same thing for oxygen, and we're going to make water from that. All right, so we're going to make this shows the heat or the enthalpy of formation of water, and we do that from these elements. We've got to put the half in front here because we only need half of that to give one oxygen. All right, and we could calculate this heat of formation. All right, well, the same type of thing can be done with an ionic compound. For example, if we wanted to do this with sodium chloride, we could do it like this right here. And the thing about this is that even though we're showing this as one step, all right, if you were to take sodium metal and chlorine gas, all right, there are several individual elementary steps that go into the formation of this process right here. And what the Born-Haber cycle does is it breaks those down into individual steps. All right, so let's pretend that we're going to make sodium chloride from its individual elements. All right, there's several steps. The first of these, so the first thing that's got to happen is that the elements in their standard state must be converted into individual atoms in their gas state. All right, so this process is called enthalpy of atomization. All right, and this is one value that's actually not found in the data booklet. So if you were to do a problem involving this would either be the thing that you were solving for, or it would have to be provided for you. All right, so these values, these enthalpies of atomization can be a little different depending on the nature of how it exists. All right, so if you have something that when the element is in its standard state, it exists as individual atoms. All it involves is taking it from whatever form it's in and going to the individual atoms in its gas phase. All right, but hopefully you realize that some elements exist as diatomic in their diatomic form, or like covalently bound to themselves when they're in their standard state. And in that case, you might have to add a coefficient to the front, because what we're interested in is figuring out the amount of energy necessary to get the individual atoms in their gas form. All right, and if it doesn't exist as an individual atom at standard conditions, you have to have that coefficient right there. All right, note that these are always positive. All right, you are actually there's a case where they would not be positive, But for the most part, whenever you're taking atoms and you're turning them, you're either breaking a covalent bond or you are turning it from its solid form and pulling those atoms apart to give the gas form. That's going to involve energy being put into the system, and that's going to make the delta H positive. All right. One case where I could say that make the argument that it's not, that it would not be positive, it would actually be zero, would be things like noble gases, something like helium. All right. And the reason for that is if helium, to do this, you're talking about the energy change involved in turning something into individual atoms in their gas state. Well, helium under standard conditions already exists as individual atoms in its gas state. All right, so there would be no energy required because it's already in that state. All right, so that's the first process that would happen if we're going to turn sodium metal and chlorine gas into sodium chloride. The second process involves turning the atoms into their ions. All right, so if we have these individual atoms in their gas form, well, to get to a sodium ion, we've got to get rid of an electron. All right, so the energy required to pull an electron away from a sodium atom is called the ionization energy, and we could abbreviate that enthalpy change like this right here. And those values are always going to be positive. All right. The opposite of that is whenever something, a neutral atom, gains an electron to become a negative ion. All right. And that's called the electron affinity, and that is usually negative. All right. The majority of these are negative. There are some cases where these are positive, but we'll deal with those on an individual basis. All right. And the last energy change involved in going from sodium metal and chlorine gas to making sodium chloride would be allowing these formed ions here to join together to make the solid material. All right. So if a gaseous sodium ion combines with gaseous chlorine ions, you'll end up making a sodium chloride crystal, all right, or sodium chloride in its solid form. And we call that the energy change that's associated with that to be the delta H, or LATT, or the lattice enthalpy. All right, this is the way it's abbreviated right here, but you would say that that's the lattice enthalpy. All right, and the thing about lattice enthalpy is that we talk about this process happening in both directions. All right, we could talk about the ions joining to becoming the salt. All right, in that case, lattice enthalpy is the amount of energy that's released when that happens. But we could also talk about the reverse of this. All right, taking sodium chloride and breaking the ions apart to give the individual gaseous ions, and in that case, your lattice enthalpy would be positive because that would require energy. Okay, notice that that's the same lattice enthalpy that we talked about in the solubility problems. All right, and notice here it's a positive value because here we're showing the solid material breaking apart to make the individual ions, whereas in cases where the opposite occurs, when the ions come together to make the solid, that's going to be just the opposite. Energy is going to be released when this happens. All right. So in a Born-Haber cycle, the way that it's generally depicted, and I know that this can be a little look a little busy at first, is to show these things happening individually. So let me break this down to hopefully make it make a little bit more sense. All right, the place you're always going to start, focus on this part right here. All right, this shows this right here shows the elements in their elemental condition under standard conditions. All right, so we've got sodium as a solid, we've got chlorine Cl2 as a gas. We're going to have to put this coefficient right here because we only need half of that to give the amount of chlorine atoms required. All right. So as we're going up here, as you go up, that's energy going up. If you go down, that's energy being given off. All right. So we know from heats of formation, if you take the elements in their natural states as elements and you allow them to form the compound, we call that the heat of formation. So going from here to table salt, that would be the heat of formation of chlorine. All right. But what we're going to do in this cycle is we're going to show how the individual energy changes occur that allow us to eventually get there if we studied all those steps individually. All right. So the first thing that would happen is that we need to take sodium in its metal in its solid form and get it to sodium metal as individual atoms in its gas form. All right, notice it's not an ion here. It's still a neutral metal. It still holds on to that valence electron, but it's just going to be the individual atoms. All right, that's going to be the delta, the atomization energy, all right, of sodium, which is plus 107 kilojoules. All right, notice it takes energy to pull those atoms apart. That's why it's a positive value. All right. The second thing that we're going to do is we're going to take this chlorine molecule right here, and we're going to pull it apart. All right. And so we have to put that 1/2 there because we're only interested in getting one chlorine atom. So to get one chlorine individual atom, we need to do this to 1/2 of that. All right. So all right, and so all of the atomization energies are always given, per atom that gets produced. So this would be always the case when you've got chlorine. All right, so that's going to require 122 kilojoules of energy. All right, the next thing that we're going to do is we need to take this sodium atom in its gas state, and we need to turn it into its ion. All right, so so the way we draw this, and you might have noticed this, is that even though we're doing one thing at a time, but we're always carrying along the things that don't change. For example, here, when we went from here to here, we showed this thing right here changing, but the rest of it just stayed the same. All right. So what we're doing here is we're just going to be taking sodium and turning it into Na plus the electron that gets given off, but we're just going to bring this chlorine gas along. All right. So that the only energy in going from here to here is the energy required from going from this to this right here. All right. So that's the ionization energy of sodium, and that would be this value right here. So the next thing that we're going to do is that chlorine atom is going to accept an electron to become a chloride ion. All right. So in going from this step right here down here, it's only these two things that are going to be reacting with each other. So the sodium ion right here just comes down here unchanged. All right, so when the chlorine accepts that electron, that's the electron affinity of chlorine, which is going to be this value right here. And again, electron affinities are generally negative, which means heat is going to be given off when they accept electrons. So now we're at this point right here, and the only thing that needs to change is that these gaseous ions need to basically arrange themselves, come together, and form that pattern of alternating ions, which we commonly refer to as a crystal of an ionic compound. All right, and those are generally highly exothermic. All right, they give off a lot of energy when that happens. All right, so this is the value right here. That's the lattice energy of sodium chloride. And so what this allows us to do is to say, well, we could calculate what the heat of formation of sodium chloride is if we know what everything else is, because whether you're going straight from these elements directly to sodium chloride, or if you're going through this kind of convoluted route where you're breaking them down into the individual steps, in both cases you're starting from this starting point and you're eventually getting to this end point. And the only question is how you get there. All right. So this value right here, the heat of formation, would be equal to the sum of all these other parts. And if you add them up, you can calculate this, and there should be a kilojoule after that, which would be the heat of formation of sodium chloride. All right. One thing you could do is you could put a little knot, a little degree symbol right here, and that when you do that, you just put kilojoules per mole. All right, because that knot means you're doing it per 1 mole of that compound.